For the compressor work, or the compressor indicated horsepower, so that will be is equal to, so indicated horsepower is equal to 11.64 kilowatt. So this is kilowatt. Then so it will be divided by the conversion of the horsepower, so that will be 0.746. So this is kilowatt. Okay, so converting that one, we have the indicated horsepower, which is equal to, so we have 15.6 horsepower. So to get the mechanical efficiency, so we need to determine the compressor brake work. So which is your brake work is equal to the output of the motor. So that will be the given. We have your 18.8. 18.8, so that will be the input of the motor, 18.8 kilowatt. And we shall multiply this one with the motor efficiency. So we have the given motor efficiency, which is 92%. Okay, so we have the output of the motor, or the compressor brake work, which is equal to, so we have 17.296 for that value, 17.296. So this will be our kilowatt. Now for our mechanical efficiency, so that is the ratio of indicated work divided by the brake work. Now our indicated work, which is already being calculated, we have, that is so that is 11.64. That would be 11.64 kilowatts. So this is kilowatt units, then all over divided by the brake work, which is the 17.296. So this is also in kilowatts. So we have now our mechanical efficiency is equal to, so we have the value of 67% for the mechanical efficiency, or should we say 60, that will be 67.3, sorry for that one, percent. Okay, so next we'll be computing the compressor volumetric efficiency. Now for the volumetric efficiency of our compressor, so that will be equal to the volume 1. So this is all over divided by the volume displaced by the compressor. Now for our B1, or the volume displaced at point 1, so we have your equation, which is your B sub 1. So that will be equal to the mass flow rate of ammonia. Then we shall multiply this one by the specific volume of ammonia, B1 at point 1. So when you say point 1, at this side, at this point, okay, going back, so we have the mass flow rate of your ammonia. So we have 2.009 kilogram per minute. So let's try to substitute that one in our equation. So we have here 2.009, so that will be kilogram per minute. Then I'm gonna multiply by the specific volume. Now the value that we have here, so since here we have only density that is given, so but we can compute that one also, we can use the density. So given the density, so at point 1 we have 0.9, so that will be kilogram per cubic meter. So we all know that the specific volume is a reciprocal of their density. So what I'm gonna do is I'm going to divide that one. So since it is a reciprocal, so this is 1 divided by the value of 0.9. So 0.9, that will be kilogram So density, the unit, we have kilogram per cubic meter. Then we can cancel out from here the common units. Your density will be cancelled out. You can cancel out your density here. So here your density cancelled out. Okay, then density, but the mass will be cancelled out. So we have cubic meter. What is left is cubic meter per minute. So we have now the value which is equal to, so I have the value which is equal now to, that is 2.23. So the units will be cubic meter per minute for the volume flow rate that we have. Now next we need to compute the volume displacement, VD. So your volume displacement, which is equal to the equation of pi over 4, we have d squared, that is the diameter, then multiplied by the length of stroke, and we have your RPM multiplied. So we have now pi over 4. Now let's take a look what the diameter of the piston there. So examining the problem, so we have twin cylinder, so that will be 2. Single acting, okay, and we have 15 centimeter, 20 centimeter, and you have your RPM. So we have the diameter, which is 15 centimeter, and we have your length of stroke, which is 20 centimeter. So we'll try to use that one. So we have multiply here, so the diameter, so that will be 0.15. So converting that one to meters, so that will be 0.15 meter. Then we're going to square this one. Then multiply it by the length of stroke, which is 20. That will be 0.2 in terms of meter. We're gonna convert that one. Then we have the RPM, so that will be 320. Okay, RPM, revolution per minute. Then that is twin cycles. I'm gonna multiply by 2 for the cycles. So we have here cycles, the unit of cycles per minute. So try to use our calculator here. So we have the value which is equal to, so we have the value of 2.262. So that is 2.262. So the unit will be so square, we have cubic meter per minute. Okay, so we have the units, which is the volume displaced. So substituting that one here to our equation, so I'm gonna substitute here directly. So we have 2.23, so that will be your cubic meter. And on this one, cubic meter per minute. Then all over divided by this is 2.262. So this is cubic meter per minute also. So I'm going to cancel out the common units here. So cancel this one and this one. So we have now the units for the volumetric efficiency, which is equal to, so what I have is 0.98985. Okay, or let's say this is 98.5% for the volumetric efficiency. So we have already computed the volumetric efficiency. Next, we're going to compute the COP, or coefficient of performance of the cycle. Now for the coefficient of performance of the cycle, so we have the heat on the absorbed on the brine, or the refrigerating capacity. Then we shall divide this one by the work of the compressor. So going back to the values of our refrigerating capacity, so looking back, so we have the value of 2,197. So I have here 2,197. So this is kilojoule per minute for the units. Then it is all over divided by the work of your compressor. Then for the work of our compressor, we have this value 698.6165. Okay, so that will be 698.6165. So we can cancel out here the common units. So this is cancelled out. And finally, using your calculator, so we have the COP, which is equal to 3.114 for the COP. So we have already completed the COP of the cycle. Now next question is make a system heat balance. Now for the heat balance, so let's check for the heat input in the system. So I will be starting with the compressor. So for the compressor, we have the corresponding work, which is 698. That will be 698.6165. So that is kilojoule per minute. Okay, now for our evaporator, so if you could still remember, we have the refrigerating capacity of our brine. So we have here 2,197. So that is 0.12 kilojoule per minute. Next, we need to determine the pipeline from evaporator to compressor. So looking at our schematic diagram here. So pipeline from evaporator. So we have here your evaporator going to the compressor. So starting from here, so that will be the enthalpy at 0.1 to 0.7. Enthalpy 1. Okay, at starting from 7 to 1. So at that point, so we have here the change in enthalpy from 7 to 1. Or also referring to our pH diagram. So that will be 0.7. So we have here 6. Here we're 7 to 1 at this point. That pipeline. Now for the Q, or the heat gain in absorbed or heat rejected, that will be from 0.7 to 1. So that will be equal to the mass flow rate of your ammonia. Then we shall multiply by this one by enthalpy 1 to change enthalpy from 0.1 to 0.7. Then we have the value, which is your mass flow rate of your ammonia, which is, so that will be mass flow rate of ammonia 2.009 kilogram per minute. Now for the value of enthalpy 1, we have 1470. So this is 1470. Then minus the enthalpy at 0.7. So for 0.7, we have 1445. So this is 1445. So we have the units of kilojoule per kilogram. So we can cancel the units here, kilogram. Then we have the heat loss or heat rejected at this point, or heat loss that being lost in the system of pipeline. So we have the value of equal to, so we have the value of 50.225. So this is 50.225. So with the units of kilojoule per minute. I'm so sorry, this is the heat input. Sorry about that. It's the heat input to the system. So correct me from that. So next, we need to determine the pipeline from the condenser to the expansion bath. So looking back to our schematic diagram. So from condenser, the pipeline, condenser to the expansion bath from 4 to 5. Okay. So that will be the heat from 4 to 5. So we have the mass flow rate of ammonia again here. So the mass flow rate of ammonia, then we shall multiply this one by the change in enthalpy from 5 to 4. Okay. So for the mass flow rate, so that will be 2.009. That will be kilogram per minute. Then for the value of enthalpy 5, so looking to our data here, enthalpy 5, we have 351.45. So this is 351.45. So minus your enthalpy at 0.4. So we have value for enthalpy at 0.4, 341.76. So this is 341.76. So with the units of kilojoule per kilogram. So we're going to cancel out our common units here. This one. Then we have now your heat 45 for the pipeline. So we have the value of 19. This is 19.46. Okay. So this is the units of kilojoule per minute.